Welcome back, ladies and gentlemen. We're talking about what's called an Atwoods machine now. If you recall from your lab with this unit, you were utilizing what was termed a modified Atwoods machine, where the cart was going across the horizontal surface and you had a mass hanging by a string over a pulley, and gravity pulled that mass down and the cart was pulled across that surface. Well, a true Atwoods machine is basically a pulley arrangement, two masses hanging off of it. The pulley is a fixed pulley, and normally what we're going to do with Atwoods machine like problems is we're going to consider a couple things. Number one, the pulley is massless, and so is the string. And there's zero friction. Now, right away, both of those are absolutely not true in real life. But we deal with what are called ideal pulleys and ideal situations quite often, and so we're not concerned about the mass of the pulley. Later, we actually will look at this, and we'll still sort of talk about zero friction, but we will actually incorporate the mass of the pulley and see why it makes a difference. But anyway, for now, it's massless. The string is also massless. There's no friction. Well, what else do we have here? We have this beginning arrangement. Let's call this mass 1 and mass 2. And, well, let's identify a few things. First, let's just say to ourselves, what do we know? Mass 1 will be greater than mass 2. And what that means is when this is released, when we let go of that one, 1 is going to fall and 2 is going to rise, just like that. And the distance that 1 falls is the same distance that number 2 will rise. Okay. But they're connected. We can say, because they're connected, that both masses have the same acceleration. Okay. They're connected objects, and all objects that are connected will accelerate at the same rate. They're forced to because of that connection. Now, we have a choice of coordinate systems. Coordinate, that's an A, sorry, system. And so we're going to pick coordinate systems that are convenient to us. And so here's what that will look like. For simplicity, I'm going to make everything moving in the positive x direction. Well, how is that going to happen, Mr. Woods? Well, I'm just going to say, well, I have a x in that direction for object number 1. And if I look at that, the normal x, then this is your typical y, is sort of perpendicular to it like that. Not worried about the y direction, but there it is. Now, I want that means object 1, mass 1, is moving in the positive x direction. I want mass 2 moving in its positive x direction, so I'm going to go, well, there's positive x, make an x, sorry, for mass 2, and the y direction here would therefore be like that. Okay, and I should mark those. And is this valid? Well, sure it is. All that means is everything's moving in the positive x direction. That will be convenient for us, trust me. Okay, we chose our coordinate system, actually 2 systems. There's something else. Okay, and this is going to be hard to deal with. I'm not going to do a full explanation of this particular item, but the tension in the string. What about that tension? It's the same at all points. It says is. Same at all points. The tension in the string here is the same as the tension here, is the same as the tension there, is the same as the tension up here on the pulley. Not talking about that thing. We don't even know if that is a string or if that's a bar or what. We're ignoring that. We're concerned with the string that is connecting the 2 masses only. And the tension is the same at all points. That totally matters for us. Okay, now, and something I really don't have to write down is that, well, since we have different masses, then they weigh different amounts. Well, duh. Okay, but what does that mean? Well, since they weigh different amounts, gravity's causing different things to happen. Gravity is what's causing 1 to fall and 2 to rise. And that sounds strange that gravity is causing that to rise, but that is literally what's going on. So the question that we're going to try to solve, all right, what is the acceleration of the system? What is the acceleration of the system? Okay, we can solve this. I should label a few more things in the diagram before we move on. So I know that there is an acceleration here, and 1 is accelerating downward in the positive x direction. 2, so that's the acceleration of object 1. The acceleration of object 2 is upward, but that is also the positive x direction for that particular piece of the system. All right. And there will be tension in the string, so I'll just label T is the same there and there. Okay. This is what we're solving. The acceleration is our goal. Right away I have forces acting on objects. I'm going to want to do some free body diagrams, right? So here we go with that. Let's do M1. Free body diagram of mass 1, well, dot, and I'm not concerned with anything in the y direction. And this is a little strange, but there's our x-axis. So x is in that direction in this diagram. I have the weight of M1, weight of 1, and I have a tension in that string. Remember that on mass 1, tension is an upward force on that string. Now, how long do I draw this arrow? Well, consider this. Without getting too formal, just give it a little thought. It's accelerating in the downward direction. That means the downward force has to be stronger than the upward force. So I draw the upward arrow smaller or shorter. I'll give it a little bit shorter there. Tension T. And that's a force. So I put the little arrow above it to help us remember that. Right away I can do some sum of forces statement, some Newton's second law statement, sum of forces in the x direction. Well, that equals a mass, in this case it's mass 1, times an acceleration. All right, but what are those forces? Well, those forces are the weight, and the weight is in the positive direction this time. Positive is down. So the weight of 1, and now the tension is up. That's the tension. And this leads to, or is equivalent to, mass 1 times the acceleration. All right, remember that acceleration is downward in the positive x direction. What about mass 2? Free body diagram of this guy. We have a weight now, but we know that the mass of 2 is less than the mass of 1. So the weight of 2 will be less than the weight of 1. How much less? Well, I'm not sure, but I'll draw it a little shorter. Like that, maybe. Weight of 2. And now the tension, well, the tension is the same at all points in the string. So I have tension upward. I have to draw this arrow equal to that. But here's something I know. I'm going to get that one right. I got this wrong. That arrow should be shorter, yeah? So, if, well, okay, I'm just going to go with it here. Make that a little shorter. How do I, maybe even shorter than that? Okay. There's my weight. Here's tension. And now, why am I concerned with that? I want to make this arrow shorter. Well, it's certainly already shorter than that one, but I have to make it shorter than this. And the reason is that this mass is accelerating upward. And so just giving it that thought, I need to realize that the upward force has to be larger than the downward force to produce that acceleration upward. Do my Newton's second law. Oh, I forgot this label. That's my x direction for this diagram, right? Second law statement, sum of forces equals or is equivalent to the mass, which is mass 2, times the acceleration. What are those forces? In the positive direction, I have tension. In the negative direction, I have the weight of 2. And that's equivalent to mass 2 times acceleration. Okay. So we're good here. All right. This is where things get interesting. There's a technique, a mathematical technique, that we're allowed to use when we have multiple equations. We can add the equations together and see what we get. And I'm going to do that. I'm going to add these two things together. There's a nice thing that happens. So let me show you this. I'll just take this one, 1 minus the tension equals M1A, and I'm going to add this equation to it. Tension minus weight 2 equals M2A. Adding equations together. We don't often do this in this class, but here's a perfect example of this possibility. We're allowed to. There's nothing wrong with that. There's no rule that says we can't. But notice something interesting. We have positive tension and negative tension. The tension goes away. It cancels out. And if you think about what's going on with this system, I'll come back to that real quick. Think about what's going on here. Why does the tension cancel out and not affect the end result? Well, the tension is a force that is internal to the system. It's not caused by anything that's outside of this system. It's caused by that pulling on that. And it's all inside. That's one way of looking at this. So it should cancel out. It should not affect the end result, which is our acceleration. So what do we have? Well, I'm also going to break up weight into mass times gravity. You'll see why. I've got mass there, and it's going to be helpful. So weight 1 is M1G, and I'm subtracting weight 2, which is M2G, and so I have M1A plus M2A. Okay, I'm getting toward the bottom of the page. Let me get this going here. I'm going to be consistent here with the colors. And I'll just I'll rewrite that so I have that conveniently on the same page. M1G minus M2G equals M1A plus M2A. Okay, I've got those two equations combined into one. Tension canceled out. It is not anything that matters in terms of our acceleration. Really what I want to do, though, is I want to sort of solve for A, don't I? And so, well, G cancels, or not cancels out, but factors out of this. M1 minus M2 times G equals, A factors out of that one. M1 plus M2 times A, and I'm solving for A, so I'm going to divide both sides by M1 plus M2. M1 minus M2 divided by, and this is how it's usually written, M1 plus M2 times G is equal to my acceleration. The acceleration of that system is proportional to G by this factor, so we have to give some very special thought to what we see here. Is this an equation worth memorizing? No, not necessarily. Understanding how to get there. We used a lot of very important skills to get there. First, and we'll come back to talking about this, but I want to remind you how we got there. First, we recognize an ideal situation, no friction, no mass in the pulley or the string. We identified, and this actually is kind of important, that M1 is greater than M2. Okay. So both masses have the same acceleration. They're connected objects. They must accelerate at the same rate. And we chose coordinate systems that allow them both to be accelerating in the positive x direction. Tension in the string tension in the string is the same at all points. Sorry. And that's an explanation all in and of itself. If you'd like to hear more, come and talk to me. And it leads us to this. I just skipped a whole bunch. It doesn't lead us to that. Well, first we have two objects with forces acting on them. We should free body diagram those things. When we free body diagram stuff, we should write Newton's second law statements that match those diagrams. And those second law statements expand into what we see here, including the weight and the tension on each side. And now here's where the fun began, because now if we stop there, then this is a bunch of skills you should already be developing, you should already be getting pretty good at by now. Mathematical trick of adding the two equations together, just combining them, and we saw that the internal force of tension goes away. And here we go. So what is the significance of this? Well, let's do a little line so we can separate this a little bit. Let me ask you some questions first. What if M2 was greater than M1? What would we see? Well, it's clear that with M2 larger than M1, we get a negative value here, and therefore that would reverse the direction of our acceleration. We get a minus sign for our acceleration in this coordinate system. Instead of A in the positive direction, A would be in the negative direction with M2 larger. Same thing over here. Instead of A in the positive direction, A would be in the negative direction with M2 larger, right? So that's sort of easy to reason out. Then A becomes negative in, no, it's not a minus sign, that's just like a marker. Then in that same original coordinate system, then A becomes negative. Well, what if, this is almost silly to ask, what if M1 equals M2? What then? Well, okay, M1 equals M2. You get a 0. And anything times 0 is a 0. So then acceleration is 0. There is no acceleration. The system will sit there because everything is balanced out. Okay, so those are some interesting questions to ask. Not too hard to reason out those answers. But consider this now. This is worth diving into. Switching colors for you. What is the significance of this equation? Look at it mathematically. A is going to be proportional to some things. A is proportional to G based on this ratio, but G is a constant. It might be better to say that A is proportional to different things in this fraction here, because that is a constant. Let's say that. A is going to be directly proportional to, well, what's the top of this fraction? It's the difference between the masses. Directly proportional to the difference in masses. Okay, so what does that mean? Well, if you have a larger difference, then you get a larger acceleration. Totally. And that's testable. You can even just demonstrate that and see that without taking any measurements. You can observe that. Well, what if you quantify this a little bit more? Well, what if you double the difference between the masses? So 2 times the difference. What does that lead to? Well, that leads to twice the acceleration. Okay, so we can say a couple things from that relationship. We can also, however, say that, well, A is also proportional to, well, what's this? This is the sum of the masses. This is our total mass, but look at this. This is in the denominator. So it's proportional to the inverse of the total mass of the system. Okay, and now what does that imply? Larger total mass. Well, how does that affect your acceleration? You get a smaller acceleration. Smaller acceleration. You could even quantify it a little bit more. You could say, well, what if you have 2 times the total mass? Then your acceleration is half as large. You get half the acceleration that you had before. And so on. Real important relationships to understand from just looking at the equation. A is directly proportional to that difference, and it's directly proportional to the inverse of that sum, which is what we've said here. That way of looking at something like this, that way of looking at this mathematical relationship is powerful. You want to be mathematically minded and logically minded when you are dealing with these types of things. All right. Well, that's it for now. Thank you for watching. I'll catch you next time.